submissions yet, but okay. So I thought what I'd do actually is just give a very brief idea of the solutions to these three problems, not details at this point, because I think it'll break the flow of going forward. And then maybe this afternoon put something up on the wiki for people who are interested in looking in a more detailed way at the solution. So let's just quickly look at the three problems and give you an idea of how they're solved. So in this case of the first part, this was the proof of Novikov's theorem. If you remember, the updates of the algorithm are given in this way. This is the perceptron algorithm. So if it makes a mistake on one of the examples, then you add that example multiplied by its label to the weight vector, and you continue until you get correct classification. Then the theorem is to show that the number of updates. This isn't working too well, is it? Is that okay? Yeah, okay. Then the theorem is to show that the number of updates is bounded in this way, and the hint was to bound two things. One was the size of the weight vector after the tth update. So if we think of wt plus 1 squared, that's of course the inner product of wt plus 1 with itself. Can everyone see that at the back? Is that okay? Yeah. But we know that wt plus 1 is given by this update rule, so we just plug it in. We then use the linearity of the inner product to sort of compute the components of that, and the first component is wt inner product with itself, which is of course just the norm of wt squared. We then have the cross components, and we get 2 yi we can take out of the inner product wt comma xi, and then finally we get this one with itself, which the yi's are plus or minus 1, so they can, when squared, they're equal to 1. And so we just get the norm of xi squared. Now, because this example was misclassified, we note here that this first middle term here is actually less than or equal to 0. That was the condition under which we made the decision to update. And so this is less than or equal to just dropping that term, wt squared. And this one, of course, is, by our assumption, bounded by r squared. So this is plus r squared. So at each stage, the weight vector can increase by at most r squared, and so this is less than or equal to t plus 1 times r squared after t updates, after t plus 1 updates, since it started with the 0 weight vector. That was our assumption here. So that's the first inequality, and the second inequality is to bound the inner product with this w star of wt plus 1. And again, we use exactly the same technique. Plug in the update rule and see what happens. And we get, of course, the inner product at the previous stage plus an extra bit, which is yi w star comma xi. But yi w star comma xi is actually the margin of the example yixi with respect to this w star, which is the assumed example which has a margin of gamma. So that here we have it, yi w star xi is greater than or equal to gamma. So this is actually greater than or equal to W star, comma, WT plus gamma. So now, with those two inequalities, the contradiction comes from the fact that the weight vector is not increasing too much in size, but its inner product with W star is increasing all of the time, and those two facts are going to contradict each other at some point. In other words, there's going to be a point where there can't be any more updates, and just the way to, sorry, I just should say this is therefore greater than or equal to, since this started again at 0, again t plus 1 times gamma. So if we just now start with, at this point here, and take that actually squared, and I'm going to do it with t rather than t plus 1, that is less than or equal to W star WT squared by that first inequality there. Then I'm going to use the Cauchy-Schwarz inequality, which makes this less than WT squared, because remember W star was norm 1. And then I'm going to use this inequality here, which is less than or equal to t times r squared. And there you have it. You just divide through by t and by gamma squared, and you have t less than or equal to r squared over gamma squared. So that gives you the bound on the number of updates of the perceptron algorithm. Okay, so that's the first. That'll be my mobile. I haven't switched off. Sorry. Thank you for reminding me. Okay. Give me a second. Okay. So now to maybe the last problem. The second problem was the hardest. The last problem was this question of how many ways you can actually generate, how many different weight vectors you can generate with these sparse dual approximations, if you remember. Maybe I can just show it on quickly here. So if we imagine taking these sparse linear combinations where the alpha i's are integers, positive integers, and their sum is at most, or is equal to b. So we have essentially m slots, and we're asking how many ways we can put b beads into those slots, allowing us to put more than one into an individual slot. So this is just a combinatorial question. So let me just indicate a very simple way of viewing a solution to that. So essentially, if we view those m slots here as pigeonholes, and we're going to put some balls in. Some of them won't have any balls, and some will have more than one, and so on. Now, what I'm going to do, so this is, if you like, corresponds to alpha 1, and this would indicate that alpha 1 was equal to 2, because there are 2 balls there, and so on. Alpha 2 would be 2, and alpha 3 would be 1, and alpha 4 would be 0, and so on. And this would be alpha m here, which would be equal to 2 in that case. Now, what I'm going to do is put a sort of blank line on the bottom here with empties in. So sort of space at the bottom of the slot. And now what I'm going to do is read off this sequence from the left into a single line in which I start at the first ball and read to the bottom. So in this case I get dot dot blank, dot dot blank, dot blank, 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 dot blank, and so on, and I finish with actually dot dot, because I'm going to actually ignore that one there. The final one will be ignored. Now, what I maintain is, now this of course is now of length m plus b minus 1, because remember there were m blanks here and there were b balls, and I actually dropped off 1, so it's m plus b minus 1. And now clearly here we have, in these m plus b minus 1 slots now, we have b balls placed, the b balls that I placed. Okay. Now what I maintain is there is a one-to-one correspondence between putting b balls into this sequence of m plus b minus 1 slots and putting b balls into these pigeonholes. And I've shown you how you convert a pigeonhole allocation into an allocation into this length m plus b minus 1 sequence. To get the other way round, given any sequence in here, you simply start at the left, and whenever you start filling this pigeonhole here, and you fill it until you reach a blank, and then you move to the next pigeonhole. So in this case, the 2 dots indicate that those go into the first. If I was doing it this way now, those 2 blanks, those 2 balls go into the first pigeonhole. Then there's a blank, so I move to the second pigeonhole. There are 2 there, so I put them into that. There's a blank, so I finish that one. Then there's a 1 ball in the next pigeonhole, and then there's a blank, so I move to the next one. There's immediately another blank, so I don't put anything in this pigeonhole and go immediately to the next one. Another blank, so that again is empty, and then there's one here, and so on. And however you put the balls in, you can perform that operation, and you will exactly fill up a certain b balls into the pigeonholes, and there's a one-to-one correspondence. You can see, I think, quite readily. Now, the reason for doing that is it's now very easy to, the actual way of counting the number of ways of putting b balls into m plus b minus 1 slots is just a standard combinatorial m plus b minus 1, choose b. So that's the result. I gave it in a slightly different form because actually I used the fact that that is less than or equal to I equals 0 up to b of m plus b minus 1, choose I. So I've increased it by adding in some extra ones below, and then I've used the same bound that was in Sauer's lemma to say that this is less than e times m plus b minus 1 over b to the power b. That's just a bound that is used in Sauer's lemma to get the form that we used in the equation. So that effectively takes care of that one. Okay? And do stop me if there are questions or you want me to clarify anything. Okay, so the third one, the second one now is undoubtedly the hardest, and probably should have been awarded more points. But I'll give you an indication of how it works. So if you remember, the problem for the second one was the following. We had to convert the problem of approximating this WSVM outputs to within gamma on 2 into a classification problem. Okay, and the hint was add an extra dimension. Okay, so here the trick is as follows. So let's just to make the notation clear, assume we have the WSVM, and on xi its output is equal to yi. This is now a real value, right? This is not the label, this is a real valued output. This is an equation here indicating the real valued output. Of course, because we're doing classification, we would assume that this was bigger than the threshold if this was a positive example and less than the threshold if it was a negative. But we're not worried about where the threshold is. We're just worried about approximating the actual real valued output. Okay. So now our trick is as follows, that we're going to actually augment the WSVM, as I indicated, with an extra dimension, and we're going to put -1 in it. Okay? And now, for each example, we're going to create 2 new examples, xia and xib. The reason we need 2 is one's going to be the one that guarantees that the output of the learned weight vector is not too much above yi, and the other is that it's going to not be too much below. Okay, so the xia is the one for above, so it's going to have the following: xi itself as the first part, and then it's going to have yi plus gamma on 2 as its second component, and it's going to be a negative example. And then the second one is going to be yi minus gamma on 2, and that's going to be a positive example. Okay, so now if we look at some weight vector that correctly classifies these examples, let's call it w, wn. So I've separated out the main part of the weight vector from its final component. And let's say it correctly classifies this example first, and I'll call this w hat here in the usual way. So w hat, comma, xia less than or equal to, well, that's going to be, because it's a negative example, that's going to be less than or equal to 0, but let's work out what it is. So it's first w, comma, xi, and then it's wn times yi plus gamma on 2. Okay, and now what I'm going to do is divide through by minus wn, and I'm going to get w over minus wn, comma, xi is actually plus minus yi plus gamma on 2, and by our assumption this is less than 0. And so that implies that minus w over wn, comma, xi is less than yi plus gamma on 2. Okay, so actually the weight vector we're going to use is this one here. So it's slightly different from just the output of the... I mean, it is, as a result of the output of applying the perceptron algorithm, you will have a sparse representation of this, and that will convert into this weight vector here. And you can see it abides, it satisfies the requirement that its output doesn't go that much more than gamma on 2. Okay? And similarly, I could plug in, and if you use for the other one, you'll show that it actually has output slightly above minus gamma on 2. Now, in doing this, the other thing that you need to take care of are the fact that the weight vector has been augmented, its norm has changed, and similarly, the value of the radius containing the points is no longer the radius that contain these points in the inputs, which might be, say, r squared. You've now got this extra component. Now, I don't want to go into the detail of that. As I say, I'll put it up on the slide. I have to on the web, on the wiki place this afternoon. I have to admit that the 8 in this here in this formula here is probably a little optimistic. I think it's more like 26 when you work through all the details. Okay, so I hope that didn't put anyone off, but there were some probably sleight of hands there, and in fact that 2m should be 4m in the under the log there. So there's a few details to work out, but hopefully that gives you a flavor of how it's done. Anyway, I don't want to spend more time unless there are any questions on that technique, but hopefully you've got the idea of how it would work now. Any questions? Good. Okay, so let's move on, and what I wanted to delve into today are concentration inequalities, and this is not, as I indicated, levels of alcohol that are legal for driving. This is about a modern attempt to bring together actually very interesting work that's been going on in more probability, classical probabilities, into learning theory. So there's been a lot of study of the behavior of distributions, and in particular when they are so-called concentrated, and this has become seen as and very shown to be very relevant in trying to analyze learning systems in this statistical learning framework. So I want to give you a flavor of that, and in particular the main sort of goal today is to lead through to Rademacher complexity, which I think has, once you get the hang of it, is actually a lot easier to work with, and potentially I think something that people might pick up and use in particular applications and analyses. So I'm hoping to give you a sort of, if you like, user's guide to how to apply Rademacher complexity, in the hope that you might find this useful. But I think also, as I believe some of the things we saw yesterday, I think you'll enjoy some of the ideas and the techniques that have been developed to apply these ideas in learning. So hopefully there'll be some fun to be had on the way, maybe some applications that you might make of this stuff later, and of course you'll get a few more words into your vocabulary that you can use at those cocktail parties. So okay, so if we're looking at statistical learning, it's concerned with reliability and stability of influences made from a random sample. That's sort of where we started yesterday. And if you remember those distribution functions that I plotted when looking at the size of the sample for learning paths and windows, and how they sort of started very, very concentrated, very tight, and then as I took a smaller and smaller sample, they sort of got more and more sloppy in the way they behaved, and eventually, it became very unreliable to infer anything. And concentration is precisely that property of having a distribution that is concentrated, in the sense focused around the mean of that distribution. And as I said, they've been the subject of study for some time. As a very classical result actually of Hoefting is exactly of this type. So I wanted to just briefly remind you of that, or show you it if you're not familiar with it. And it leads very nicely into the sort of next, perhaps slightly more advanced concentration inequality that I'd like to show you. But here's Hoefting's result. It relates to the mean of a set of random variables, x1 up to xm, which are assumed to be independent, which I failed to put on this slide, but if you've got a pen, write independent on there. Basically, the assumption about the variables is really quite weak. All we assume is that they are bounded within a range ai to bi, each independent. I mean, they're different. There's not assumed to be the same, identical in that sense. So they're independent but not necessarily identical. And the inequality bounds the probability that a particular instantiation of this random variable Sm. So in order to compute Sm, we pick a random x1, a random x2 up to a random xm, we add them up and we divide by m and we get a value out. So imagine, one possibility would be you've got a sort of a one-dimensional input and you're just computing its mean. So you take an m-dimensional sample and compute the mean, and that's Sm for you. Okay, and what this is trying to do is compute the probability that mean in a particular instantiation is significantly different from its expected value. So in those plots I showed, if you remember, I had the mean as a little circle and then the distribution. So this is precisely computing the probability that you're going to have samples significantly deviated from that circle. And what this is saying is that the probability of that being greater than or equal to epsilon is less than or equal to some exponentially decaying function. And notice that the exponential decay depends on epsilon, so as epsilon goes away, we're going to get smaller and smaller values. M squared, now that M squared actually is a bit deceptive because there's a sum up to M on the bottom here. So if you imagine these all being the same, then you'll get this sum equal to M times some constant. One of the M's will cancel, but there'll still be an M on the top here. So as the sample size increases, it's going to shrink the the range of that splay in the distribution, and it's going to become concentrated around that mean. Okay, so that's the sort of flavor that we're looking for: exponential decay away from the mean of a distribution. Yeah. Okay, so with that flavor, let's move to how concentration can help statistical learning theory. And the results come from what are known as concentration inequalities. So again, that's a really good phrase to use. Yeah, I've thought about the concentration inequalities and I think we can do something here. So the main one that's most used is due to McDiarmid, and that's the only one I'm going to show you. There are many others, and names that you want to mention are Talleyrand. That's a good name to mention. But also Lugosi and others, Bousquet, of course, and so on. I'm sure Olivier will be mentioning more of this as well. Have very interesting results which can be applied in learning theory as well. What I mean is slightly stronger under certain conditions concentration inequalities. But this is, if you like, the sort of vanilla version, and is very useful, and in many applications is just what you need. Okay, so I want to try and really give you a flavor of this, so we'll go through it quite... it looks a bit of a mouthful when you see it like this, but it's really, I think you'll find quite acceptable. Firstly, note it's a very similar form to Hoefting. You've got the exponential decay here, you've got the mean and the particular instantiation, okay? The difference is that it's more general. It's not here the mean of the distribution. It's some function of these random variables, so that the random variables could be in any set A, and the function takes n of those examples and maps them into the reals. So it's some function, and you could imagine taking a sample and computing, I don't know, the generalization error of that sample or something. So, quite a complicated function of those examples. The function, so this is sort of, if you like, the sample estimate of that function. This is the expected value of that function. So again, would apply ideally to those diagrams I had, the mean and the sort of splay. And this would be one element in the splay, and this would be the mean. And you're asking, what is the probability that the splay bit is epsilon bigger than the expected value? And we're getting something that's going to look useful when it says, exponentially small. Okay, so here you might say, but where's the m squared gone? Well, that's because the CIs here are effectively what was bi minus ai divided by m, so that's sort of the m squared. It is exactly the same form. In fact, we'll see Hoefting is just a special case of this, where we use the function Sn as in place of f. So this is sort of identical to, it's a pure generalization of Hoefting. Okay, so what is the condition that is required? Well, basically what we need to show is that if we take any set of values, x1 up to xn, so you may be confused by the notation here, small case, lowercase, uppercase. So this is a tradition that varies from field to field, but often people use uppercase to indicate a random variable, meaning you're going to sample that and get a value out, and lowercase for the actual values that you get out. Okay, so these are actual values that might be generated by x1, and these are actual values that might be generated by xn. I'm assuming they're all in this set A. And what I've done here is take any set of actual values, okay, and I've taken the same set here, except that I've substituted xi for xi hat. So what I'm saying is, given any allocation of the variables, if I swap one of them for another variable, how much can the value of f change? And what this is requiring is that if I change the ith input, it must be bounded by c sub I. Okay? So it provides a bound on, if you like, the variability of f as you change individual elements. but it's a soup over all possible choices, so it must apply whatever the other variables are. If you change this one, you can't change it by more than Ci. So it's quite a strong condition, and much of the advanced concentration inequalities are about weakening that condition and using other estimates that indicate the range of change in a slightly weaker way. Okay, so the first question, I guess, is, how does Hoefting come from this? And perhaps that's something that you might want to just spend 2 minutes convincing yourself on a piece of paper if you've got one. Substituting that function, how do you actually get back to what Hoefting gave us, which was that? Okay, so do you want to spend just 2 minutes doing that? So there's Sm. It's just the average. Notice it's 1 over m sum of xi. That's critical. So what you have to do is work out what Ci is in the case of Hoefting. How much can that average change if you substitute a value for the ith component? Remember, the ith component has this range bound ai bi, right? So if we substitute that, so on. Okay. The f functions. You just replace f by minus f, and you can actually get both inequalities holding, so that you actually can bound it from both sides. But I won't go into the details of that. Okay, so that's where that 2 comes from, and you can apply the same technique with McDiarmid and put the absolute values here and put a 2 here. So it's just a simple union bound to get that. Okay, now the next thing I think is worth looking at briefly as well is inverting this. So if you imagine, we're getting sort of used to doing this now, whenever we have these sort of bounds on probabilities of things going wrong over samples. So notice I should emphasize again, if I look at this here, this actually is, in my old notation, p to the n. You know, this is a sample probability here. It's the probability of a whole sample doing something. being less than this, well, we know what we always do with that. We set it equal to delta and we invert it, right? I mean, we're just dab hands at that, so we just plug it in and do it. So if you plug that in equal to delta here, you do the usual thing, take logs, take the minus sign over, you get log 1 over delta, you get 2 epsilon squared, sum ci squared here, you bring over the sum ci squared, and divide by the 2, so you've got epsilon squared is sum ci squared over 2 log 1 over delta. And the only difference we've got here that we didn't have before is that it's epsilon squared, not epsilon. And that's where the square root comes from that I indicated in the, if you remember, the case of errors in the VC dimension case. So that corresponds to a square root entering in on the right-hand side here. There it is. Sum ci squared over 2 log 1 over delta. And we also bring over this, so you can then bound for the particular sample is less than the expected value of the function plus this sort of little term that involves log 1 over delta. And now we can, that applies now with probability 1 minus delta. So it's the usual idea. We bound the probability of things going wrong, you know, that we're too far away from the mean. And so with probability 1 minus delta, we're closer to the mean than that. Okay? So this is almost always the way in which one wants to use things in a learning context. Frequently, we, in our case, will be using a sample, in which case these will be identically distributed, and typically, therefore, the CI will be the same, and very frequently also it'll be something like C divided by N, where N is the number of examples. And if we just plug that in, we can see that the form we get then is this, where the N comes on the bottom now because the CI squared was on the top. Notice that though we had 1 over N squared, the sum is from 1 up to N, so we get N copies of C, and one of the N's therefore cancels. So we end up with C squared divided by 2N. Okay? Now that's always the form we're going to get with this square root in the rest of what I'm going to describe today and in the Rademacher results. So it's slightly unsatisfying. I'll mention something more about that a little later. The results we had yesterday typically didn't have that square root. The square root, of course, makes the bounds much less tight. You know, if you had a bound of 1 in 100, you take a square root and it's a bound of 1 in 10, which is, you know, 0.1, which is not so good. But the flexibility and the, of course, when you're far away from, you know, rather larger errors, then the bounds, the square root is not so significant. Okay, so my first application of these ideas, and this is like a warm-up of Rademacher complexity, is something referred to as stability bounds. Now, in the book that Nello and I just recently published, we use stability to just mean sort of reliable estimation, so it's slightly confusing with this use of stability, which is a technical term introduced by Olivier Bousquet and André Lissieff. And they introduced this very neat idea, and it allows a fairly direct application of these concentration results. So I think it's a nice way to start, sort of lead into using the ideas, see how they're used in an example, and then we'll tackle the Rademacher case, which is more general. Okay. So they introduced this idea of a uniformly stable algorithm. So it's interesting, they're actually trying to bound the performance of a particular algorithm. Most generalization bounds, the ones we looked at yesterday, and the Rademacher bounds, are going to be so for apply for any function. So sort of it doesn't matter what the algorithm does, provided it gets a good result, then this will hold. This is actually looking at the particular algorithm, and it says it's uniformly stable with respect to a loss function L if this holds for all S, for all training samples. We apply the algorithm to that sample, and we apply it to the sample with the ith element thrown away. That \I means that we remove the ith element. So it's a bit like doing leave one out. That's the idea here. And what we have to check is that if we apply the result of that function to a new example, the loss associated with that and the loss associated with this when we apply it after removing that example is for all test examples less than or equal to beta. So it's a fairly strong requirement, but surprisingly many algorithms, and even the SVM, in the case of the one norm SVM, you can get a bound on this beta. I'll show you later. So that this is actually remarkable that it is so applicable. It does make sense in some respects in that you wouldn't want things to change too much just by removing one example. But of course, if you just take a hard margin SVM, this doesn't apply. You can have quite strong changes in the output. Okay. So this is the assumption. Now I'm simplifying down what they've done. They've actually done quite a number of different variations on this definition in their paper. So if you're interested, you could follow up and read that up. I think I've put references to all of the papers that I've made use of in the back and many others as well. Okay, so how do we approach this using this concentration inequality strategy? Well, what we're looking at is trying to estimate the difference between the expected error, expected loss of the learnt function. This is A of S, is the function returned by the algorithm. This is the loss and its expectation under the underlying distribution. And this is its empirical loss. This is the loss on the training set. I'm using this hat notation to denote the expectation on the training set. So it just means the average of the training set losses. If you see E hat from now on, it always means that. Okay, it's just work out the loss on the training set and take the average of that value. So this is the sort of what we can tell from the training set. This is what we want to know about. This is the true performance on unseen data. And so D of S is the difference between those two. So we're going to sort of go for it, just try and get a bound on that. And we're going to apply McDiarmid's theorem to this D of S quantity. But we're going to look first at how much this can change as a result of a substitution of one example. And we're then going to look at how much this can change from the substitution of a single example. So this, we're going to first treat this as, we're treating this as our f of s, right, in McDiarmid's theorem. But we're going to see how much this can change first, and then how much this can change, and then add the two together for the total amount of change. So, of course, maybe I'm jumping too quickly, but if you want to apply McDiarmid's theorem, the critical thing is to get a bound on this quantity here, right? So what we're trying to do is say, okay, this is D of S. This is D of S with one of the examples replaced by some other example. And what we want to try and do is find out how much it could change as a result of making that substitution. Okay. And what we're going to do is we're going to bound that in two stages, one for the first part of D of S and the other for the second part of D of S. So let's look at the first part. So here's the expected value minus the expected value with the ith example replaced by a new example. I'm denoting that again by superscript I. Well, we can think of replacing an example by a two-stage process in which we remove the old example, and that gives us this set S\I, and then putting in the replacement. When you're sort of repairing the car, you take out the faulty component, put in the new one, and that gives us the difference here between these two. So the change can be broken down into the amount of change when we take the guy out, and then the amount of change when we put the new guy in. And of course, we can basically just, the definition of uniform stability that they used actually is just a bound on this change, right? Because it's an L infinity bound on the amount of change that you can make between any example, and this is the expectation of a random example, so obviously it's going to be smaller than beta, and similarly here, so it's 2 beta, right? Okay, I mean, if for any example the change can only affect its value by beta, then the expectation of over a random choice of that example can be at most a change of beta. Yeah? Maybe I didn't say that very well, but hopefully it's okay. Okay, so now in the case of the empirical, it's a little bit more complicated in that here we've got the empirical and the empirical with the substituted example, and again we remove it and then replace it, so it's the same idea. But and we get the 2 beta because again, you know, the amount of change here on the all of the other guys is at most 1 over m in this estimation. The only problem is that the one example that we removed will no longer be part of this estimation here. And so we essentially, this 1 over m comes from the fact that we've removed one example here and replaced it with a different one here, and we can estimate that sort of directly. Actually, as written, this probably isn't quite correct, but they have a nice trick to show that the actual replacement of that one example, since the loss function is bounded between 0 and 1, so you actually get a change of at most 1 over m. Okay, I'm not going to give a super detailed account of this. Again, I'm trying to give you a flavor of how this application works. Okay, so now we've bounded how much the 2 parts of d of s can change. So we can now give a bound on how much d of s can change, and that is 4 beta plus 1 over m, right? The 2 parts, 2 beta plus 2 beta plus 1 over m. Right? Plug and play, right? What do we get? So remember C, this is C sub I, right? And so all we need to do is to plug in that C of I. Oh, God, I've gone over time, haven't I? Shit. Okay, so, right. We'll come back to this. Take a break. Okay, we'll start again at 10 past.